Welcome to stage 1 of the roadmap that is helping you master LLM-based applications. This is the first stage of 8 stages roadmap that is moving you from a curious builder to master AI engineer. In this video, we're gonna laying down the groundwork together. LLM engineering is not a guesswork, but it's a strict engineering. And if you want to design any complex agent or retrieval pipeline, you must understand that how large language models are actually thinking. Stage 1 is providing for you this exact mental model, vocabulary, and engineering intuition that help you in future to build reliable, scalable, and production-ready AI systems. If you skip the foundation, your application will break in the production. In this masterclass video, we're gonna break down 4 topics together. The first topic, how large language models are working. Second topic, the limitations of the large language models, or in abbreviation, LLMs. Third, how to choose the right model specifically for your own use case. And fourth, design patterns for LLM applications. Let's dive into this. We are in the foundation stage. What do I mean? Foundation stage is the very first stage of 8-stage roadmap that I designed for 2026 to help developers master LLM-based application. And the very first topic of this stage is how LLMs actually work. I'm not going to the architect of LLMs in detail. It may sound boring to you, but I would like to answer 7 core questions many people ask when they are exploring generative AI. Let's go to 3 of the questions for now. But before going to questions, I would like to mention I'm hearing a lot about let's ask ChatGPT this question or not. The case is that GPT is one of the large language model families, and there are more variation of these family models like Llama, Mistral, Claude, DeepSeek, Gemini, and etc. that you can use them for your own experimentations. Some of you already may heard of these large language model families. This is just for more information for beginners. The very first question is that what is a language model? Language model means understanding the human language, and the people already familiar with topic of natural language processing in artificial intelligence know what it literally means. If I'm gonna simplify it, a language model is a system that predicts the next word, or more technical word, the next token in a sequence. The core of it is probability machine, that when you give any text to it, it estimates which token would be the output as the next word with highest probability. The example here in the image, you can see the boy went to the. If such an input will be given to LLM model, it will come up with some probable outputs like cafe, hospital, playground, park, and school, and see which one has the highest probability, and that would be the output of the model. Here, playground has the highest probability, and that would be the output of model for this specific sentence. Well, now that we got the point of what is a language model, let's go to the next question. What makes a model large? A model becomes large with different factors and reasons. One of them is the number of parameters that they have. The backbone of large language models is neural network. And neural network, when they got trained on massive data, they have billions of parameters. And these parameters, each of them reach the point of the weight during their training till they got the last version when it comes to the market and you start using them. These number of parameters, billions of them, make these models large. Another reason is that they got trained on massive text corpora. Many numbers of books, articles, code, web data, and other sources are ingested to these models when they got trained. And they have also the ability to process long sequences. The previous designs of the NLP models, they didn't have such ability to process long sequences, but these LLM models, they could. We talk about the parameters. I would like to give you some examples here. We have tiny edge devices like Gemini Nano with 1.8 billion parameters, Llama 3.2 1 billion and 3 billion parameters. We have a small mid-ranges of the LLM models. Mistral 7 billion, Llama 3.2 can have 11 billion as well, and Pfeiffer from Microsoft 14 billion. There are also large workstation models with like Llama 3 with 90 billion parameters, DeepSeek version 3 671 billion parameters. Even we can have enormous supercomputer LLM models that they can reach till 1.8 trillion parameters. Well, now let's focus on the third question, which is transformer architecture. I mentioned transformer as the engine behind LLMs, but that doesn't mean LLMs are using transformer architecture as it is. They got inspired by transformer architecture. Later I will explain more. I would like to now focus on 4 key components of transformer architecture that help them to understand the human language in long sequences. One of them is self-attention. Self-attention, paying attention to specific words at each time to find the relationship between words, even when the input would be longer and longer, even your text become longer. The other point is positional encoding. Transformers cannot process text sequentially. That's why positional encoding should be there to mention where each word is located in the input. Multi-head attention layer is about stack of attention layers that each of them try to extract the patterns separately or independently, better to say. They're extracting the entities in the text input as well. The output of it will be given to feed-forward layer, which try to find deeper representation of information using the entities and patterns already extracted. This is the architecture of the transformer layer. The left side you will see the encoder and in the right side decoder. Let's at first focus on the encoder because that's the part right to understand the context of the input. When the input will be given to embedding layer, embeddings model transform the text into digits would be understandable for computer, and we have positional encoding which gives the position of each word in the input side. I mentioned why it is important. Then the input will be given to a stack of attention layers in multi-head attention. They try to extract the patterns and entities, and it will be given to the next layer, which is feed-forward. They try to find the relationship and meaning and deeper representative between patterns and entities. Then output of this encoder will be given to decoder. Decoder use this to understand what would be the best prediction or next token by given input from the encoder. This is exactly the part I would like to emphasize, that the LLM models only use the decoder side because they are generative models. They're generating or predicting the next word or token. They don't have anything to do with the encoder. That's why the LLM models have only the decoder side. But this architecture helps the LLM models to understand the context, and they work way better than previous models like recurrent neural networks and LSTMs. I'm going to talk about what they cannot do, but that doesn't mean that their limitation would be forever. For sure, technology is improving day by day, and part of it or all of it will be solved in future. You already work with LLM base most probably and already know that they transform how we are interacting with technology. But that doesn't mean that you need to ignore the fundamental limitations, especially if you are developing LLM-based applications by yourself. It's necessary to have the knowledge about fundamental limitations. Let's go to the very first one. LLMs don't understand the word they predicted. In my previous video, I mentioned that the architect back of the LLM base is just pattern recognition system based on the huge corpus of the data that they are trained on. It means that they are generating the next token based on their given text that are already given to them, and they are using statistical patterns to predict the most probable token for the given text. It means that they don't really know all the facts, and this is exactly the problem that led them to their biggest weaknesses, which is called hallucination. Yes, hallucination is their second weakness. In this video, I'm going to talk about hallucination. Probably you heard about this word, but more accurate definition of it is that the LLMs can confidently generate wrong answers. That's true. LLM can generate incorrect facts. They can fabricate the citations. They can call non-existent APIs, and etc. Because these models, they got trained to be fluent. They are not trained to be truthful. They don't have any ability to verify the generated information or go to external resources and check the reality. This is exactly a significant challenge for high-stake domains such as law, medicine, finance, and science, because truthfulness matters to these high-stake domains more. Well, I already gave a hint about the large corpus of the data that LLM models are trained on. That's exactly leading us to this third limitation, which is called limited and fixed knowledge. What I mean by that? LLMs are trained on fixed snapshot of the data. It is huge for sure, the number of the data that they got trained on, but still it's a fixed snapshot of the data. It means that whenever the training got cut off, they don't know exactly what's happening after that cutoff. Or better to say that their knowledge is not completely up to date. They cannot by themselves go to the web and search for the facts and realities until the time you are explicitly connecting them to the external sources. And when you are even pairing them with external source for better retrieval systems, the model use your data from your external source to format it in such a way that you want as output, but still the LLM models remain static, the same as it was before you were using them. The fourth limitation is that no real-time understanding or memory the LLMs have. It means that they don't have persistent memory to know that what happened in previous interactions with the user in your system. They completely operate within the fixed context window that you have. So probably they will lose part of the context of the information, especially if the information is bigger than their context window. And this actually limits how much information they can consider at any given time they are handling part of the information. And it is quite challenging, as I mentioned, when the information would be way bigger than the capability of the LLMs within the context window. Well, large language models coming from different families, I explained them in previous videos, but to just name a few of them: GPT, Llama, Claude, Mistral, Gemini, DeepSeek. Each of these families, they have their own models and also their own versions. That's not the only case. As research grows in this domain, more and more models will be added to this list, and it would be quite overwhelming for you to find out what would be the best model for your own use case. You need a proper, profitable strategy that make a force multiplier to your project and also faster iterations. Otherwise, you end with no model application to the production. Please consider this step quite serious in your application. Choosing the right model is super important for your architectural design of your application. If you choose any wrong model, it can lead you to high cost, even without having anything in the production. It can happen your performance would be quite low, whatever metric you have for your performance. For instance, poor accuracy. Maybe you can have hallucinations, or maybe you still have compliance risk with the model that you already chose, and it doesn't let your model to go to the production. Even in worst case, it doesn't let you scale your system to larger scale. That's awful. That's why it's important to consider this step in your LLM-based applications. And I designed this guideline for this specific content in this week to break down these three questions: how to choose the right model, which criteria matter most, and how to filter out other models before going to deeper experimentation. The full content of this guideline is, again, in my Substack channel, specifically for paid subscribers. And the very first step out of this guideline is to start with your use case. It is important. You need to be clear which use case you have, because these different use cases, they need different strengths from LLM models. I just brought some specific common use cases, for instance, retrieval augmented generation, customer support automation, coding agent, reasoning heavy tasks, summarization, classification, creative writing, multi-step agent workflow, real-time chat, or voice assistant. Each of these use cases need different strengths from LLM models. The second step in this guideline is talking about key criteria for choosing the right model. I define 9 criteria in this guideline, and 3 of them will be mentioned in this video. If you want to have full access to the 9 criteria, please go ahead with my Substack channel. There you can find the full content, and specifically for paid subscribers. The very first criterion is about task performance and capabilities. What I mean by that: for instance, in case of the reasoning ability, if your model needs multi-step reasoning or workflow agent, you need to go ahead with the heavy reasoning LLM models. Smaller models are really struggling with multi-step reasoning. That's why it's important. Or in case of knowledge depth, I'm not talking about the information they got trained on, but I'm talking about how they are interpreting the information. For instance, in RAG or retrieval augmented generation models, when you are retrieving information or chunk from different sources and you are combining them together, your model should be able to interpret this information very well and then integrate them very well in larger chunk of the data or summarize it, give it back to your user. You need to consider this. Or in case of the domain specialization, you need to be sure which model is trying very well on relevant information to your own use case, because in case of advancement optimization, it makes your job easier when you have models relevant to your own use case. For instance, the cloud model are really good and trained very well in coding. And if your use case is about coding assistant, you can go ahead with cloud models. But for other domains like medicine, law, science, any of these cases, you need to check it out. The second criterion is about context window requirement. What I mean by that: those ones that are work with large language models know each model, they have their own context window, which means within that context window, the model is able to work with the information. And if in any contact of your LLM with your data, you are using big data, large chunk of the data, you need to go ahead with the models with larger context window. Otherwise, the smaller one would be better. The third criterion is about latency. Please consider this as an important criterion for your own model, specifically when it goes to production. For instance, if your use case is about real-time response, the user expects quick response from your model, you need to go ahead with the smaller models. Or if you have any large model, you need to distill them or quantize them so that the response time becomes shorter. Consider these ones when you are thinking of the best model or right model for your own application. Now let's go to the topic of design patterns for LLM-powered application. Please consider that I'm not focusing on agentic systems, it's about non-agent systems. Later, we will talk about it in future about agentic system. But now I'm going to talk about the very first pattern, which is the agent pattern. This pattern is quite a lightweighted version of the agentic systems. It's about the system that they design what to do next. And it's not about how to do it. How it is working. When any input is coming from your user, the LLM, any type of the model that you consider, will determine what would be the next action, which is exactly based on the user input. It will decide whether it should call a tool outside, whether it should retrieve information from the bunch of information you have backside in your own system, whether it should go search on the web, and etc. It is useful when you want to have fully controlled decision-making system and you want the LLM just pick from really quiet predefined actions that you already have. So it would help the system to have quiet, predictable behavior and would not go runaway approach. But why this type of the pattern is useful? It's quite simple to implement and it's quite easy to debug because for each of the steps that you have, you can create different functions in your code and then easily see where is the problem for each part of the process and debug it. And it also avoids any risk of runaway agent loops. It would not get into the loops. It is quiet, following the process that you define for your own system. It is useful for customer support flows when you have very well structured workflow. And in case of search experiences, you want to lead your user very well during the steps of the search. I prepared a sample here. For instance, you have the website that you sell some products there, and you have also the guarantee of repairing the products. So imagine you want to implement a repair request assistant with your own LLM. The follow is here. Imagine a user would ask any request to you. You would like to at first be sure that the request from the user is about the repair. When you are sure about it, it would go to the next step. What is the order number that the user had from your own website? So you have a database with a list of the order and detailed information, and you want to be sure that the order number is correctly matching with the one you have in your own database. When you got sure about the order, you want to check whether the user is the real user of you in the database. And when the user verification is completed, then you would like to ask which type of the product that specifically assigned to that order they want to be repaired. Because it can happen, one order can have multiple products. Then when it is done and the product is clear, then you need to check in database whether that specific product has any guarantee or not. If there is a guarantee for your product, then you would schedule an appointment for them. But if the guarantee is expired, then you will tell the user this is the cost for you and would you like to pay for it or not? If yes, then you will go again to schedule appointment for them. So it's quite simple. All of the steps clearly defined. And later we will go to the code that I explained to you how is it going in real coding practice. Well, now let's go to the cool topic of our part, which is coding. We will define the assistant as a class for our code, which is the repair assistant here. We define the initial function inside of this class. What would it include? It would be the state at first, because we're gonna start the process of workflow with the very start ask request. This is the very first step for us, and then we would have access to the database. If you want to design your own complete database, you can replace this one. For just simplicity, I just put a sample in the dictionary type, and the structure is like all of the orders, they have order number, they would have the postal code of your home. For the verification, we need this part. We have list of products that are ordered within that specific order. For instance, here we have two products. One of them is a coffee machine. The other one is toaster. The coffee machine has guarantee, thus the cost of the repair is 0. The toaster has the guarantee valid false, and the cost of it is 40 euro. This is the initial function. I will explain the next functions later, but let's go to the main code. In the main code, we will call this class. To create an instance of it, we call it agent. When we are asking the user to input their request, their input will be assigned to user parameter, and it will be given to our agent instance, and we'll call the function of the process. Consider here it is a loop. Why it is a loop? Because we're gonna go through multiple steps with the user, and for sure we need their input. That's why we still keep it in the loop of true. For the very first step, we just get the request, and let's see what's going on in the process function. The process function is exactly after the initial function, and because we already initiated, the very state that we have is ask request, then if the state is ask request, it will call the function of handle request. We have other steps one by one that I will explain it. Let's go through the very first one. If the state of our own assistant is ask request, it will call the handle request. In handle request, whatever user input we got, we just add some pre-processing step inside of it. You can add it on your own. And we will check whether there is a repair word inside of the request or not. If it is the case, then the state would be the next step, which is asking the user about order number, because we are sure that the user asked about repair. So we will say to the user that you requested a repair. Now it's time to enter your order number. But if it is no repair, then I would say, okay, if you have any repair request, just consider including this word of repair. This is the way I'm managing the input from the user and have more control. For sure, it's not a really correct way when you want to put it into the production, because I'm using a hard coding of repair. You can use it more advanced level, but it's just the idea giving you that how you can manage different steps. Okay, now that the state is changed, we are assuming the user is asking about the repair. We will go to the next step about asking order number. When we give it to the user here in the loop, that with the response that you already asked about the repair, now we will go to the other step, which is about order number. And the state already changed to order number. Then the state is order number, and we need to call the handle order number function. In handle order number function, when I'm getting any input from the user, we call it order ID. We will check it that this order ID exists in the order or not. If there is such a order, we will put it as a context of our code. But if it is not the case, then we will say enter a valid order. And if it is a valid, we already assign it as a context of the assistant, then we will check for verification of the postal code. That's why the state is changed here. Again, I should repeat here that the postal code is for verification, to be sure that it's the same user asking for the orders we already have in database or not. The question of the postal code will be shown to the user and ask for it to enter the postal code. Since our state is ask postal code, when the process function is called in the main function, it will call the handle postal code function. In handle postal code function, we will check whether the user input postal is the same as the postal code we have in our own database or not, in our context especially, because we are focusing on a specific user. Then if it is the case that they are different, then it will start from scratch and go back to the start of asking the request. But if it is matched well, then it will go with the guarantee check. You want to ask the user that which type of the product from that order they want to be repaired. So this will be shown to user. Your postal code is verified, which product you want to repair. And when the user inserted the input, the process function here will go with handling the check guarantee function. In handling check guarantee function, we have user input as a product name. We have the order also in database that we put it as a context of our work. Then for all the products we have in our orders, we want to be sure that this product is the same as the product name that user entered or not. Here you can have different type of pre-processing. I assume with just simple lowering all the characters, we would reach the same, but maybe it can happen you need to add extra pre-processing on your information. Then here, if it is the case that we could find a match between different product names, then we will check if that specific product has any guarantee or not. If it has any guarantee, perfect. The user doesn't need to pay anything for it. Then we will change the state to ask for availability of the user. So we will just tell the user that the guarantee is still valid and enter any date or availability to schedule an appointment for you. But if there is no guarantee, what would happen? We need to quite be honest with the user that your guarantee is expired and the cost of it is 40 euro if they ask for the toaster. And do you want to proceed or not? This is exactly the same process as happening if you have phone call with your own user. And you can see here that they are different states. It's like a branch of decision. Assuming that we have the case of the cost, then it will go here to the function of handle repair cost confirmation. And we will be sure that if the user asks yes, why, okay, sure, all of these text that can show the user want the product to be repaired. And if that's the case, then it will go to the same process of asking for availability. Otherwise, it will start from the scratch. But in this case, it's going again to the repair availability as the previous step that we had. And if the user is asked about availability, the function of handle repair availability, just put it the start state, the next one, because this is done for this process. And what would happen? We say, okay, within your input, we found your availability for a specific, we will schedule this timeline. This is just the idea to give you how the logic is working. For sure, if you want to make it in your production code, you need to add more processing steps here, either for processing your input or processing output. But that's just giving the hint how the design should be that help you to have full control over your own workflow. And it will finish the step and go from the start. It got quite simple, and you can make it way better. But I hope that it helped you how to design the agent pattern to help you have fully control over your own decision making, especially in any real case you have with customer service. It is necessary to keep them satisfied. Well, we covered the code. I hope you really enjoyed how is the process of making a repair request assistant for your customer service, which is really amazing how we can control all the process and limit any problem that LLMs can bring us to the reality. And that wraps up the core foundation for stage 1. You already know the vocabulary and intuition till some degree to build LLM applications properly. And remember, I mentioned till some degree. A stage 1 handbook of mine has deep dive information, comprehensive in detail with coding. In the first topic of how large language models are working, you get to know answer of 7 questions that people are facing when they are exploring generative AI. The second topic that is about limitations of the LLMs, you get to know 15 limitations. The third topic, how to choose the right model. You get to know additional factors to consider. And fourth topic, design patterns. You get to know 4 design patterns for LLM applications. Click the link below, get the handbook, and build your foundations today. And don't build your LLM applications isolated. Join my community at Shiva Tech Hub. Ask your questions. I would love to give you feedback and help you in your journey. Besides of that, the members of the community, they have the advantage of getting early updates, extra resources, and free newsletter from me. Join me there. I would love to be more in direct contact with you. Thanks for watching Stage 1 video. See you in Stage 2.
Grab the links to our practical handbooks in the description below to catch up fast. And make sure to subscribe to stay ahead.